Welcome back, students. In the previous class, we have discussed the kinetic energy, its types, and work energy theorem. How the kinetic energy is related to the linear momentum. All these conceptual questions and the derivations we have completed in the previous class. Now, in today's class, I am going to explain the second type of energy, that is potential energy. In many daily life examples, you have seen the cases of potential energy, and now today you will recognize how they are related to potential energy. Students, you have seen that a toy car, when we move or wound the spring of the toy car, and after that we keep it on the floor and the car starts moving. In that spring there is a potential energy, and that potential energy of spring is converted into the kinetic energy, and that's why the car is moving. Second time, you have studied the case that the water at a very height kept in dam, and at that water is released from that height and on falling on the turbine and then through the generator the electricity is produced. Here the potential energy of the water at height is converted into the kinetic energy to move the turbine, and that kinetic energy is further changed into electric energy. So that is the potential energy at the height. So you can say that the energy in the body, due to its position, due to its configuration, due to its stretching or compressing situation. Suppose you are stretching a spring or you are compressing a spring. These kinds of energy is known as potential energy. Let us write down the definition first. The potential energy. Potential energy. It is the energy possessed by the body by virtue of its its position or configuration. Its SI unit is joule, represented by capital J, and CGS unit is arc. The dimensions are dimensions, that is the form of any work, that is M1 L2 T minus 2, that is force into displacement. Here the examples of potential energy. First, energy stored in the spring of a toy. After releasing, that energy is converted into kinetic energy, that is energy stored in water at large height, and energy stored in elongation or compression of spring. Then energy stored in a body which is placed at the top of tall building. Okay, you can write down these examples in your notebook. The type of potential energy is gravitational potential energy, And gravitational potential energy, you can write the amount of energy possessed by the body possessed by the body due to its position above the surface of earth. This energy is only due to the gravitational force. This is due to the gravitational force. Now consider the object of mass m is lifted from Earth's surface to a height h, and for h very smaller than the radius of Earth, value of acceleration due to gravity is kept constant. Now some work has to be done. This is the body. This is the body of mass m, whose weight is acting in the downward direction due to the gravity force, and now you are moving this body to some height above the Earth's surface. Now this is here, and h is the height through which it is moving. The force of gravity is acting on this. Against the force of gravity, some work has to be done, and that work is equivalent to the potential energy. So what is the amount of that work done? You know, work is equal to force into displacement, and the force is here the weight of the object, and that is mg, and displacement is h. So we can write it as this work done is equal to mgh, and this work against gravity is equivalent to potential energy. This is denoted by capital U, and you can write it as mgh is equal to W. This is the formula for the potential energy. And if h is 0, it means at ground, at the Earth's surface, then potential energy is 0. If this is first case, this is second case. If h is maximum, then potential energy is maximum, that is mgh maximum, keeping the acceleration due to gravity constant. Got it? Now the next topic is conservative force and non-conservative force. Non-conservative force. Now let us study first the conservative force. Suppose any object is moving along these two paths from A point to B point, and we have to calculate the work done along these two paths. If this work done is found to be equal, the work done from A to B is equal to the work done from A to B. This is along path 1 and this is along path 2. If these are equal, it means this is independent on the path followed. This is depending on the initial and final position. This type of work is known as conservative force. The force in moving a body from one point to another have equal work done or the force or the work done depends on the initial and final position of object. Then it is known as the conservative force. One more point is also there. If this object is moving from A to B and then along the different path it is moving from B to A. Now this is the closed path. What will be here? The work done along A to B along the first path is equal to the work done from B to A along the second path, but the direction is opposite. You will write the minus sign for the opposite direction, and here you can write that work done from A to B along path 1 plus taken on the left hand side B to A along the path 2 is equal to 0. If the force is obeying this condition also, in that case you can also say that the force is conservative force. You can write the conclusion: if the work done along the closed path you can say the total work done along the closed path is 0, then the forces are of conservative nature. Now what are the examples? Can you suggest me some examples? I can suggest you. First is the gravitational force. It does not depend on the path. Second is the electrostatic force. And now the non-conservative force. This is the opposite of conservative force. If the work done along the closed path is non-zero, the total work done is non-zero, or it depends on the path followed. Then the forces are non-conservative forces. Got it? Now what are the examples जो path पे depend करते हैं? The frictional forces में हर केस में वर्क डन डिफरेंट होगा, पाथ पे डिपेंड करता है. सेकेंड इज द विस्कस ड्रैग फोर्स. Viscous drag force is the friction force of liquid. So these two forces are of non-conservative nature. Understood? After studying the conservative and non-conservative nature, let us prove that the gravitational force, I told you the example na, gravitational force is conservative. Prove that the gravitational force is conservative in nature. So what we have to do? We have to prove that the force which is acting on the body is giving rise to the work done, and that work done depends on the only initial and final position. It is not depending on the path followed of the object. Okay, let us consider for this. Consider an object of mass m is raised to some height, that is h, from the ground against gravity. If it is moving against gravity, what will happen? Then some work has to be done, and that work is equal to the force acting on the body and the displacement. Suppose this is the body of mass m placed at the ground level, and the weight is acting in downward direction, and you are going to raise the body up to the height h. Here this is the height h from the ground. Now the force is equal to this weight, this is equal to mg into the displacement h. The work done is equal to mgh. This is equation 1. This is the gravitational potential energy, or you can say the work done. Now consider the second case. Suppose this body is placed at ground and you are raising this body along this path, then here, then here, then you moved this body like this, and then now this body is at the height h. This is the same height, the total height h from here to here, but now you have raised this body in intervals. Suppose this height is x1, this height is x2, and this height is x3. And from the figure, it is clear that h is equal to x1 plus x2 plus x3. And this is, suppose, y1 and y2. So calculate the work done along these three paths. Suppose this point is A to B to C, D, E, and finally F. So work done, total work done will be this total work done, that will be from work done from A to B plus work done BC plus work done CD plus work done DE and plus work done EF. Now you can see, students, here in the area BC and DE, what is there? The weight is acting in downward direction and the object is moving along the horizontal direction. One is this and another in this case, y1 and y2 case. Here the work done will be 0 because the angle theta is 0, and work done is Fs cos 90 and work done will be 0. And in this case, work done will be, weight is in downward direction and height is x1. So write it here, WAB, that is m into g into x1 plus along BC the angle is 90 degree, work done is 0, plus CD, here the weight is in downward direction, body is moving in upward direction, that is mg into x2 against gravity. Along DE, the path is having 90 angle with displacement and force, and along EF the work done is mg into x3. So add all these values. The total work done is equal to, take mg constant, and x1 plus x2 plus x3 inside the bracket. Put the value of x1, x2, x3. This is mg into h. This is the work done, or you can say the potential energy against gravity. This work done is equal to potential energy. And now you can say that in these two cases, in case 1 and case 2, the work done is same. It is not depending on the path followed by the object. This is the zigzag path followed by the object, and here it is moving in a straight path. The same object is there, the same height is there. Hence we can say, hence from 1 and 2, the gravitational force shows its conservative nature. You can prove another path also. If you want to prove that the body is placed here and you are moving like this, and now the body is at point this, and now you can calculate the height. You can take h here. You can also calculate in this theta. You will find this in terms of theta. You will have the values, and this is the final expression for the conservative nature of gravitational force. Got it? What you have to do? You have to compare 2 or 3 paths, and in all the paths the work done should be mgh. Got it? Let us do one numerical on the basis of the potential energy. The question is, a frictionless ball of radius capital R is kept there. A ball of mass m is pushed down the wall from point A. It just rises up to the edge B of the ball. Then calculate the speed with which the ball is pushed down along the wall. So what is given to you? First, imagine a hemispherical ball is given to you, and R is the radius of this ball. So you can write R like this. This is point A, from where the ball is released, and the ball is moving along this path. This is the frictionless, and at this point, you know, this is the highest point from B side, so V becomes 0 here. And what is the height of the ball here? The height is R. H is equal to R here. Similarly, here also H is equal to R. So what you have to do? This ball is pushed. Given the ball is pushed down, it means you have given some velocity to this ball. Let the velocity of ball is, velocity of pushing a ball is v meter per second, and height of the ball in the hemisphere is equal to the radius. So the energy at point A, energy at A should be equal to the energy at point B. So energy is the sum of kinetic energy plus the potential energy, because it is having some height as well as it is moving. This is again equal to the sum of kinetic energy plus potential energy at point B. This is at point A. So kinetic energy at point A will be, this is half, and it is given velocity v. So half mv square plus mg, height is r. This is equal to, at the point B, at highest point, the velocity becomes 0 because it will stop for a few moments. So half m 0 square plus the height is r, mgr. So you will have half m v square is equal to mgr minus mgr, or you can say this will, just a minute, It is given that the object is released from some height h. It is given from some height, so this height is h. You can say here the value is h. Correct it, because it is released from some height, it is pushed from some height. So this is h. The value is v square is equal to 2 into mg is common r minus h. If h is greater than r, then v is equal to 2 mg r minus h under the root. So velocity of pushing the ball is v is equal to 2 mg into r minus h. Got it? If numerical value is given there, then you can solve with the numerical values. For any doubt and for any query, you can write the comment in the comment box, or you can ask to me on phone also.